Hello everyone. This is the video lecture of section 5.10, first part. Okay. All right. This is the section about improper integral. What do I mean by improper integral? You learned about this formula. If you have antiderivative of lowercase f of x, capital F, then you have to do this, which is f of b minus f of a. If f of x is continuous on the whole interval, including point A and B. All right? And f of x is derivative capital F of x. Okay? If you have such functions, or actually it's better if there exists some capital F of x, which is continuous on this such and f prime of x equals f of x on A. This is better. Okay? So if you can find continuous function, continuous antiderivative from A to B, including A, including B, so that you can calculate these two values, then you can use fundamental theorem of calculus to get this value. So if your function is continuous from A all the way to B, okay, that's what you're considering. And this will also give you the area from A to B. If f of x is above dy x-axis, then that's the area of that region. Okay. Now, what if we are interested, let's say from 1, y equals 1 over x. Not somewhere all the way. Can we think about the area of the region under the graph of y equals x from 1 all the way to infinity? Okay? Can we make sense out of this? From 1 to infinity. From 1 over x dx. Right? Now, we cannot define this one because from the beginning, your definite integral was defined for a function which is defined from A to B on a finite interval, right? From the beginning, we excluded this case from 1 to infinite size. So we can't even define this definite integral. And also, there's some fundamental difficulties in understanding area of a region which is infinite in size, lengthwise infinitely long. So, is it going to be infinitely large area if lengthwise is infinite in size? Or is there any way we can make it well defined, the area, even though lengthwise is infinite? Now, in order to overcome this difficulty of definite integral being defined only on the finite interval, we can actually approach this way. Let's say, this time, going to 0 faster than 1 over x. That is, let's consider 1 over y equals 1 over x squared. Now, because our definite integral does not work for the infinite size interval, we can consider this way. Cover this. Consider up to t only. All right? I go from 1 to 10. Well, of course, it does not cover the entire region we already had in our mind. What about t equals 1,000? 1 to 1,000. Then it's getting thinner and thinner. covers a lot, but of course infinitely long tails are left. Okay, so as we cover, so this is area so far. Think about this: 1 to t 1 over x dx. This is so-called area so far function from 1 to t. We let t grows larger and larger, million, billion, trillion. In the process, do you think this, as t grows infinity, this definite integral, the area from the region from 1 to t, that value is approaching some finite number or going to infinity, right? So this is what we want to define as this integral, all right? Likewise, same thing. This one also will be defined exactly the same way. From 1 to infinity, 1 over x squared dx will be defined as area so far function and limit as t goes to infinity. If this limit is finite, then we call it this improper integral is convergent. If this limit of as t goes to infinity does not exist, then we call this improper integral divergent. Okay, so this is so-called the first type, improper integral of type 1. Let's do this. Now this is actually negative 2. Antiderivative is adding 1, negative 1, 1 over negative 1, so negative 1 over x from 1 to t. That is negative of 1 over t minus 1. T going to infinity, 1 minus 1 over t. Hey, 1 over t goes to 0, that's t going to infinity. It's getting closer and closer to 1. See? When t equals 100, 1 minus 1 over 100 is 0.9. If t equals 1000, 1 minus 1 over 1000, 0.999. See? It's getting larger and larger, but ever so slightly. In the end, as t getting larger and larger, it's increasing because still we have some positive areas. But it's so slow that you will never ever cross value 1. Only getting close to 1. Indefinitely close. Then we define that 1 is the value of this improper integral. It's convergent case. Now then, using this concept as a limit of area so far function, we define this area of this infinity long region is still finite number 1. Okay? So even though lengthwise is infinite, so that you cannot even using ruler. Ruler is always smaller than a finite size. Yet we can think of a finite area. Even though lengthwise, in certain direction, the region is infinitely long. What about this? This is ln of x from 1 to t. Going to infinity, ln of t minus ln of 1. ln of 1 is 0. ln of t, growing slowly, but still goes to infinity. So as t grows, the area of up to from accumulated area is growing slower and slower. Yet as t goes larger and larger, there's no upper bound. It stops or approach. It keeps going up, getting larger and larger. So you can choose t value to make this area so far be as large as you want. Of course, t has to go great length to make accumulated area to become very large, but still it is possible. So in that case, this is divergent. This is convergent. The intuitive way of understanding is that we are considering this area as you sweep more and more, right? Areas of our function. In order for this type of integral to be finite, your graph has to get smaller and smaller very quickly. Yes, 1 over x going to 0, getting closer and closer to 0, but not fast enough. 1 over x squared goes to 0 fast enough to make this area to be finite. All right? Yeah, when x equals 10, this is 1/10. When x equals 10, 1/100. Much smaller. So it's quickly approaching x-axis, right? So you make it, the remaining infinite tail is really, really thin, much thinner than this one. That's why the area of this region is actually finite. Okay? All right, let's formally define improper integral of type 1. In the first part, we are going to consider only type 1. A, if t f of x dx, f of x dx exists for all t greater than or equal to a, then a to infinity f of x dx is defined as t going to infinity from a to t f of x dx, provided that the limit exists, which means converges. Limit exists means that improper integral is conversion. Conversion, we say conversion. This improper integral is conversion. Being, if t to be x exists for all t less than or equal to b, then negative infinity to b f of x dx is defined as t going to negative infinity t to b f of x dx. Alright? So, this is the case where supposedly going to 0 quickly from a. So from a to t, for all t greater than or equal to a, this has to be all defined, well defined. And that value's limit, as a function of t's limit, should be finite. This case, it's going to the left forever, right? T to b, the definition from t to b has to exist for all t less than b. And that t going to negative, if that limit exists, that limit value will be our improper integral value. Provided that the limit exists, or conversion case. C. If if minus infinity to a f of x dx and a to infinity f of x dx both are convergent, then minus infinity to infinity f of x dx is defined, and that to be minus infinity to a f of x dx plus, okay? If both of them well defined and convergent, then we say that from negative infinity to infinity, definite integral f of improper integral f of x will be these two values addition. Alright? well defined, and this one is also well defined, then the entire area will be addition of those to that. Right? It makes sense. So let's consider some examples. Other than we already found that 1 over x improper integral from 1 to infinity, 1 over x is divergent. 1 over x squared from 1 to infinity improper integral is convergent. But that's not the only improper integrals we're going to consider. Let's consider some other examples. Example 1. Example 1. Evaluate A 0 to infinity x times e to the minus x dx. B minus infinity to infinity x cubed e to the minus x to the fourth dx. All right, solution A. All right, these are continuous everywhere, 0 to infinity everywhere. So this one will be just limit of 0 to t x e to the minus x dx. So let's consider this one before we take the limit as t going to infinity. So this one, we have to use integration by parts. We have to integrate this one and differentiate this so that x will disappear when we differentiate. Integrate this one will give you minus e to the minus x. So I'm going to keep x as it is. So I'm going to write that. Keep it this, integrate this function minus integrating one as it is and differentiate the other. I just wrote it integrated by part, literally the given the way it was given in the formula. And that one from 0 to t, 0 to t. That one is minus x over e to the x, 0 to t, right? Minus plus 0 to t, e to the minus x dx. So this one, I'm going to write here, minus t over e to the t minus 0, okay, minus e to negative x, 0 to t. So minus t over e to the t minus e to the minus t plus 1, all right? This will be e to the minus t minus 1, so I just issue it with minus. So, what is this? Limit. Take the limit. T going to infinity of 0 to t x e to the minus x dx of minus t e to the t minus e to the minus t plus 1. T is getting larger and larger, probably. E to the minus 100 power, e to the minus 1000 power. This one will go to 0. This one stays at 1. What about this one? This is infinity over infinity form, indeterminate form. In that case, we can use L'Hopital's theorem. This will be, I take a negative out. So derivative of numerator over derivative of the denominator. And I'm going to copy one constant 1 out. Now, 1 over e to the very large power will be 1 over a really large number. So it's going to go to 0. So it's going to be 1. So, therefore, 0 to infinity x times e to negative x dx will be 1. Because this is exactly this limit value. Alright? Now, second, B. B. So negative infinity to infinity. So from the third type of, no, it's part C of the first type of improper integral. This should be, we have to consider both cases, right? X to the 4th dx 0 to infinity. Anyway, the inside function is defined everywhere. So, to consider this one, we have to think about t to 0, x to the 3rd, e to the minus x to the 4th. And then we're going to take the limit as t going to negative infinity. So, this one, if it is u, du equals minus 4x cubed dx. So x cubed dx is negative 1/4. So this is negative 1/4 e to the minus x to the 4th. That is antiderivative. Okay? That one from 0, t to 0. Minus 1/4 e to the 0 equals 1 minus e to the minus t to the 4th. It's minus 1/4 plus e to the negative t to the 4th. Therefore, minus infinity to 0, x to the 3rd e to the minus x to the 4th dx is limit as t going to negative infinity of this expression. Well, t is negative large number, but t to the 4th, even power will make it anyway positive. Positive large with minus sign. So e to the very large negative, e to the minus million, which is 1 over e to the million. 1 over very, very large number. So this one goes to 0. So I can write this one to be, it'll be easier to understand that. E to the very large power, because minus large number, negative large number to the even power will be positive large power. Really large number in the denominator. This one going to 0, so minus 1/4. All right, for this one, you have to consider this 0 to t. Likewise, minus 1/4 e to the minus x to the 4th power from 0 to t, e to the minus t to the 4th minus 1. Minus 1. I forgot minus plus 1/4. Sorry about that. But it doesn't make any difference. Okay? So 1 plus 1/4 minus 1 over 4 e to the t to the 4th. Same thing if you take the limit. So 0 to infinity, x to the 3rd e to the minus x to the 4th dx is limit, simply said, this proper integral, improper integral is limit, t going to infinity from 0 to t, right? X to the 3rd e to the minus x to the 4th. Okay? That is limit t going to infinity, 1/4 t to the 4th, 1/4. Positive 1/4. So, this one, 1/4. This one, negative 1/4. So this will be 0. Okay? All right. Now, next example is really interesting. Really. Find the value p. Value of p. Value of p. Value of p. For which 1 over x to the p dx converges. Okay. In the introduction, we already showed that when p equals 1, the divergence already we saw that. Because antiderivative 1 over x involves ln of x, and ln of t goes to infinity as t going to infinity. Okay, so therefore that's why I suppose that p is not 1. Then, if it is p is not 1, this is actually negative p. Now, because p is not 1, the definite integral will be just power, adding 1. 1 over 1 minus p, actually 1 minus p, from 1 to t. Okay? So it is 1 over 1 minus p times t to the 1 minus p minus 1. Now, think about it. Limit of t going to infinity. In the end, we take the limit as t going to infinity. This is the one who makes a decision. T to the 1 minus p equals. If p equals, now p is either greater than 1 and if p is greater than 1, what do you get? This will be, if p is greater than 1, this is same as, I can write it as t to the p minus 1. If p is greater than 1, then what is it? T to the positive power is the numerator. T to the positive power is going to infinity. 1 over infinity. 1 over a very large number is 0. Okay? So if p is greater than 1, if p is greater than 1, so t to the negative power, 1 over t to the positive power, will go to 0 as t going to infinity. However, if p is less than 1, then you have a t to the positive power, like a t to the 1/2 or t to the 1/3, whatever. In that case, as t going to infinity, however slow it is, it's still going to infinity. Okay? Therefore, this one, 1 over x to the p dx equals 1 over, this is 0. So 1 over 1 minus p, convergence, p greater than 1, but divergence. It's not equal this or divergence. And this will be very useful. Later, we're going to compare things against 1 over x to the p power in comparison test and all. Alright? So, divergent. We have to include p equals 1 here. Strictly greater than 1 here, convergent. Anything else? Divergent. Okay? Alright, that's the end of the first part of section 5.10. Thank you.